Okay, something to note when we're talking about these chiral molecules, that the chirality center is a structural feature that causes a chirality for these molecules we've made so far, such as 2-butanol. The chirality center is this carbon. It is a chiral carbon, and it's that chiral carbon that makes the molecule chiral, gives it a chirality center. But note, chirality is a property of the entire molecule. So we're saying that this is a chiral carbon. This carbon here is a chiral carbon because it has 4 different groups coming off of it. Because this molecule has one chiral carbon, the entire molecule is chiral. Remember, when you're talking about a non-superimposable mirror image, you're talking about the non-superimposable mirror image of the entire molecule. The entire molecule is chiral. All right. Note also that having one chirality center guarantees a chiral molecule. It guarantees what we have 2 enantiomers. We're going to find out 2 or 3 chirality centers, 2 or 3 chiral carbons do not guarantee enantiomers. But having one chiral carbon means you have enantiomers. Also note that a stereogenic center is not necessarily a chirality center. When you look at our cis and trans molecules, we see that is this carbon here or this carbon here that makes the molecule cis or trans. So this is a stereogenic center because here is the cis molecule. If these two groups were flipped, the chlorine down and this hydrogen up, then it would be the trans isomer, and that would be the 2 diastereomers. So this is a stereogenic center because it's what makes our molecules be diastereomers, but it's not a chirality center because diastereomer molecules are these 2 diastereomers. This is not a chiral carbon here in either of these 2 diastereomers, therefore can't be chiral without that chirality, without the non-superimposable mirror image. All right. So how do you tell if a molecule is chiral? One, just you can make models or draw them. That might help you. Find only one chirality center, then it's a chiral molecule. Only one chiral carbon, you'll have it. The other thing is, and we'll discuss this in a later video, if you find a mirror plane in the molecule, if there's an orientation of the molecule such that half of the molecule is the mirror image of the other half of the molecule, then that molecule is achiral. All right. So now that we know we've got the 2 different isomers, we realize we need a way to name them. And so along come Kahn, Ingold, and Prelog, and they came up with the RS system of naming the molecules. It's basically what they wanted to do is say, okay, let's take a molecule drawn 2-dimensionally on a sheet of paper and find a way to name it so that we will know which one of the 2 enantiomers that it is. All right. So let's go through the rules and then we'll do some examples. The first thing we need to do is assign a priority to the 4 groups on the chiral carbon. Recall that there's 4 different groups coming off the chiral carbon. What if there are only 3 different groups coming off? Then it's not a chiral carbon and there's no RS system needed. So you're going to find the 4 groups on the chiral carbon. You can either list them A, B, C, or D. I tend to go 1, 2, 3, and 4 a lot. And the higher the atomic number of the atom bonded to the chiral carbon, the higher the priority. All right. If just so happens to have 2 of the same atom bonded to the chiral carbon, then look at the next set of atoms in the unassigned group. And those 2 groups that have the same chiral carbon. And you keep going outward until the first point of difference. What this will lead to is if you have a branched chain, that will be a higher priority than a non-branched chain. And if none of your chains have branches, then the longest chain has a higher priority. And how we're going to assign this is, for example, we're dealing with 2-butanol right here. And so if we draw it out, here's our CH3, CHOH, CH2, CH3. We see, okay, what's bonded to this chiral carbon? Well, a carbon, a hydrogen, and an oxygen. Atomic number, we see on the periodic table that oxygen has a higher atomic number than carbon. So oxygen is a higher atomic number than either of these two carbons. Hydrogen is always going to be atomic number 1. It'll always be the lowest atomic number. So hydrogen is going to give us our lowest priority. This oxygen is our highest priority since it has the highest atomic number. But what about the two carbons? What we're going to do is this. When we see the CH3 and the CH2, CH3, we're going to say, okay, here's our chiral carbon. It's the one with the OH on it and the H. What is bonded to this carbon? Well, we know the chiral carbon is there, so we're going to ignore that. What other three things are bonded to this carbon? The answer is 3 hydrogens, so we're going to write that HHH. 3 hydrogens on this carbon, HHH. What about this carbon here? What's bonded to it? Note we ignore going back to the chiral carbon, just moving outwards. What's bonded to this carbon? Well, 2 hydrogens are bonded to a carbon and another carbon. So we're going to write that CHH, because this carbon is bonded to another carbon and 2 hydrogens. So this carbon here is HHH. The CH2 over here is CHH. This carbon has a higher atomic number than this hydrogen. Therefore, this has a higher priority. It's a longer chain, and as I just said before, longer chains through this system will be given higher priority unless there's branches. So that makes this the second highest priority, this the third highest priority. Hydrogen is the lowest priority, oxygen is the highest priority. And then things get a little funky with our rules. What you then need to do is rotate the entire molecule. And note, bad news here, when I say rotate the entire molecule, on the exam you're not going to have models to do this with, so you're going to have to do this in your head. In your head, you need to rotate the entire molecule so that the lowest priority group is directed away from you. You're the observer. Direct it so the lowest priority group, the hydrogen, is away from you. The way I've drawn it here, if this is your eyeball and you are looking left here, you need to orient the molecule so this carbon is going away from you. Another way to do that, let's draw it slightly differently. Another way to do that and get the same thing for this 2-butanol is, let's see, which one is this? Okay. We have the OH coming out like this, and the H is going back that way. So here we can see already that in this orientation the hydrogen is going away from us. The OH is coming out at us. The hydrogen is going away from us in this molecule. All right. Once you have done that and you have your priorities A, B, C, D, 1, 2, 3. So I'm going to say I like the numbers. This oxygen is priority 1. I know the hydrogen is priority 4. We've said that this one is CHH, so it's priority 2. This one is HHH, it's priority 3. What you are going to do next is trace a path, draw a curve from A to B to C. So you're just going to draw this curve for A to B to C, or 1 to 2 to 3. Where, yes, I kind of went through 4, we'll ignore that. But here's my arrow from 1 through 2 to 3. Note, this path goes clockwise. If it's a clockwise rotate, if this path rotates clockwise, this is the R isomer. If the arrow drawn from 1 to 2, 3 happened to go counterclockwise, it is the S isomer. Okay. So that's Kahn-Ingold-Prelog rules. That's the way they decided to do it. So people said, okay, that works for us, and so that's the way we're going to draw these molecules. Note, what if I had drawn this molecule instead? What if I'd started with this one? It's my 2-butanol, but coming out at us, I had the hydrogen, and going back, I had the OH. How do we use Kahn-Ingold-Prelog rules to name this one? Well, let's see. We need to assign the priorities. Good news, we've already assigned the priorities. We know this is 1, this is 2, this is 3, this is 4. But note, we need to rotate the molecule so the lowest priority group is directed away from us. So how do we rotate the molecule? No, we just can't switch things. We have to completely rotate the molecule so that the lowest priority group is going away from us. Well, I have to take it like this and rotate it 180 degrees. Okay. Now with the models, it's actually easier to see. I need to take my molecule that looks like this. See how I've got the ethyl group on the right, the methyl on the left, the OH going back, and this hydrogen coming out. I need to rotate the entire molecule 180 degrees to get this hydrogen going back. Note, I've rotated this physical molecule. In your head, you have to realize, okay, I need to do just a little rotation here, which means this ethyl group is now going to be on the left. The methyl is on the right. Coming out will be the OH. Going back will be the hydrogen. So now that I've got that hydrogen back, now I can assign my priorities. And I've got my 1 here. I know my hydrogen is 4, so I don't have to worry about it. Here is 2, here is 3. Drawing my circle 1 to 2 to 3. See how it goes to the counterclockwise direction. So this is the S isomer. So the one up here is R2-butanol. The one down here, the enantiomer that I drew, is the S2-butanol. And when you're doing this and doing this rotation, hopefully you can see, I bet you didn't see it, but now you should be able to see, there are 2 ways to draw the enantiomer of the molecule. One way is to just draw the mirror image of the molecule. If you could look at this one that I drew here and this one I do here, can you see that these 2 are actually in a mirror image arrangement? If I took this molecule here and just moved it up here, I could see that these 2 are mirror images of each other. So one way to draw the mirror image is to just actually draw the mirror image. The other way is look at this one and the second one here. It's a little busy, but can you see that if this was the R isomer and it had the OH coming out and the H back, but the methyl and the ethyl are left and right, here the ethyl and the methyl are in the same. Here, ethyl right, ethyl's right, methyl's left, methyl is left. But for this one down here, I just took the OH and made it go back and the H coming forward. So when I switched the OH and the H, but left the other 2 groups where they were, I also created the enantiomer. So those are the 2 ways, the 2 best ways of drawing the enantiomer to the molecule. Way number 1, just physically imagine there's a mirror image and draw the mirror image. And I will tell you this, if that's the way you're doing it, the best way to do it is with your hands, because your hands are mirror images of each other, at least close enough. Your hand, that's handedness, mirror image. So if you're like, okay, what's the mirror image of my hand like this? If my left hand like this, what's its mirror image? It's the right hand like this. Use your hands to help you. So okay, if I have, look at this, I've made a fist and have my thumb coming up towards you. What's the mirror image of that? It is the other hand, fist, and the thumb coming up towards you. The mirror image of this is this. Note, the mirror image of this is not your thumb going backwards down. That's not a mirror image. This is the mirror image with the thumbs coming out. All right. So one way is to just use your hands and draw the mirror image. The other way that usually is easier is just switch any two groups on the chiral carbon. Here's a chiral carbon. I switch the OH and the H. I draw the enantiomer. I could have switched the ethyl and the methyl. Leave the OH coming out and the H going back. Switch the ethyl and the methyl, and that would be the enantiomer. Note, if I left the OH coming out and this H going back and switch this ethyl and this methyl, that's the same thing as drawing the actual mirror image. OH out, H back, just the ethyl and the methyl are on different sides. That's drawing the mirror image. So switch any two groups on a chiral carbon, you will get the mirror image. Okay. Now, this video is getting a little bit long, but there's a few other things we need to discuss. One thing is, there actually is kind of a shortcut. There is a little bit of a shortcut to this problem, especially if you're having problems, rotating the molecule so that the lowest priority group is directed away from you. Because what if you had an issue with that? What if you had this molecule, our R2-butanol, we had 2-butanol. What if coming out at you was the hydrogen and going back was the OH? What if you realized, okay, group number 4 is actually coming out at me. Group number 1 is going away from me. I need to rotate this molecule to get this hydrogen to go backwards. And what if you say to yourself, oh man, I'm really poor at doing that. I can't do that very well. There isn't other way around it. The way around it is ignore the first part of Rule 3. Make a mistake. Purposely make a mistake and do not rotate the molecule. If you do that, if you purposely make the mistake and do not rotate the molecule, no, we still have priority 1 here. Priority 2 is the ethyl. Priority 3 is the methyl. So let's just not rotate that molecule. Let's do this. Let's draw our curve from 1 to 2 to 3. You see that it is going clockwise. Since this curve is going clockwise, you would assume it was the R molecule. But then you say, wait a minute. I got the answer R molecule, but I ignored Rule 3. The group number 4 is not going back. In fact, group number 4 is exact opposite. It's coming out at me, which means if I didn't do Rule 3, if I don't have priority 4 going backwards away from me, that means this answer R has to be wrong, because R is only correct if group 4 is going away from me. Group 4 is not going away from me, therefore R is wrong. So if R is wrong, what is the correct answer? S is the correct answer. That's kind of it almost seems like cheating, but that's another way to do it. If you look at it and say, okay, I'm not going to put group 4 back. I'm not going to switch these two groups. I'm just going to do it knowing that the answer I get is wrong. I know R is wrong, therefore the answer must be S. That's another way to do it. And as you can see, as I drew it here, showed that R was wrong, so the answer is S. This molecule is the same as this one down here that we found out when we actually did it the right way and rotated it so they are backwards. The priority 4 was backwards. It is the S isomer. So this is S2-butanol because R is wrong because we didn't put group 4 backwards. That's another way to do it. Whatever way works for you. Whatever way will give you the right answer every time, use that method. Now, occasionally you have issues when you have double or triple bonds and you're trying to assign priority. When you do that, say you had a chiral carbon right here. This was a chiral carbon. I'll give it a little asterisk. And you say, okay, well, what's on this carbon? What are the 3 groups on this carbon? Well, there's an H on there. There's a carbon. Since it's a double bond, we say, okay, there's another carbon on there. So for this carbon, the 3 groups bonded to it, we would write that as CCH. Carbon is bonded to a carbon, the second bond to that same carbon, the second bond to the same carbon, and the hydrogen. That's how we do that. If you had a carbon triple bonded to something, that would be as if this carbon had, well, it does have 3 bonds to that thing, so this would be in parentheses Y, Y, Y. All right. Cool. Do some practice with these, and we will continue more with chirality in the next video.